Sivan Biham, which is the computer vision and machine learning algorithm developer at Healthy.io, where she works on healthcare-related products, taking them all the way from the algorithm design stage to fully implemented product with thousands of users across the world. Welcome, Sivan.
Imagine you are working on a company that develops a mobile application for flowers classification. Your client can take an image of every flower that they see, upload it using the application, and then you, given your algorithms, can tell him any detail regarding these flowers. The type, the size, the color, the smell, and even its favorite location and weather. You already have those algorithms, the first version of those algorithms, which are probably deep learning algorithms that were trained in a supervised manner, which means that in order to train those algorithms, you needed both the images of the flowers and the ground truth labels. The ground truth will tell you the true color and the true type of these flowers. Now, what we want to do is to create the next version and to improve the accuracy of our algorithms. In order to do so, we need more label data in order to train those algorithms. But we don't have it. All we have is this big unlabeled dataset that we get more and more of from production every day. So what can we do? Do we really want to label this entire big unlabeled dataset? The answer is that probably we don't want to do it. Why? Because if you will take a look at those images here for the example, you will see that several images share similar characteristics. We have several images of white flowers, several images of yellow flowers. We have even several images of the same kind of flowers. Annotate this entire dataset will not necessarily give us the best improvement and maximize the improvement of our algorithms because of this redundancy. What we might want to do is to find a method to create an algorithm that will help us to choose wisely a subset from this big unlabeled dataset, such that it will maximize the improvement and the accuracy of our models while minimizing the cost and the time of labeling this entire dataset. And those types of algorithms, what they are and how we can implement such algorithms, this is what we are going to talk about today in this talk. So a little bit about me before we continue. My name is Sivan Biham, and I'm from Israel. I came to here 2 days ago, and I'm very excited to be here in Romania. It's actually my fourth time here, but I love it every time that I come. I hold a master's degree in computer science with specialization in computer vision and deep learning, and currently I work at an Israeli startup called Healthy.io. At Healthy.io, our goal is to transform the smartphone camera that every one of us has into a medical device, so we'll be able to take medical tests from the comfort of our home. I'm part of the research team in the company, where we work on two main lines of product. The first one is urinalysis test, pregnancy, kidneys, UTIs, and the second product relates to chronic wound. As you can see here in the image, this is not a real wound, it's makeup wound, so you can be relaxed. And this is most of the features and algorithms that I work on, mainly focused on this product, and this is the main motivation behind the project that I'm going to talk about today. So let's go back to the flowers. We are going to stick to the flowers for the next of the presentation. There are not going to be wounds. As I already said, using our application, we collect more and more images of flowers using our customers. And now those images of flowers are the input to our algorithm. Let's say, for this example, that we want to calculate the area or the size of the flower. What we need to do in order to calculate this area, we have two pre-steps that we need to develop before, which is called detection and segmentation. The detection task is the task for finding the region of interest in the image. The output will be bounding box, as you can see here in the image. Those regions are areas in the image that have high probability to contain flower or any other object inside this bounding box. Given those bounding boxes, we can now develop the segmentation algorithm. The task of the segmentation is the task of classifying each pixel in the image into a given class from a given set of classes that we have, and then we can take all the pixels that were classified as flower and find the contour or the boundary of the flower in this image. Using this contour, we now can calculate the size and the area of this flower. Here you can see an example of what are labels for the detection and for segmentation. The segmentation is at the top and the detection is at the bottom. And somehow we need to get those labels. We need someone to annotate it, to draw those labels on the image. And we doesn't necessarily have the time or the required knowledge in order to create those labels. So we get the help of experts or outsourcers that help us to label all those images. Those experts are both expensive because they are experts and very busy. So what we want to do is to find a small subset as we can that will help us to improve the accuracy of our model while minimizing the size of this dataset because we don't want to be so dependent on those annotators. Okay, so we already have a labeled dataset that we used in order to train the first version of our models, and we have this big unlabeled dataset that we get from production every day. Now the question that is raised here is what we can do with this big unlabeled dataset and how we can sample it in order to improve our accuracy. The first and most simple option is just random sampling. We can take this big unlabeled dataset, sample it randomly, send this subset into our annotators, get the labels, add it to our training set, train again, and it will indeed reduce the cost and the time of labeling, but this does not necessarily maximize the improvement and the accuracy of our models. What we can see here is a linear process, which means that we don't have any connection between the current model in productions to the new subset that we are going to send to our annotators and add to our training set. It means that we are not taking into account the strengths and the weaknesses of our model when we choose a new data to train with. If we have some type of flower that we are very inaccurate on it, we are not taking it into account when we choose this new data set. What we might want to do is to use our own knowledge regarding the model and the data. This is me in the left or right, and I am very familiar with the model, I am very familiar with the data, and I can tell you for almost every image from production if our model will be accurate or inaccurate on this image. For example, if I will get those two images from production, I can tell you that I don't want to send them to annotations because I saw enough white and yellow flowers. My model is accurate on those type of flowers. I don't want to spend time and money on those images. But if I will get those two images from production, I will tell you that I want to send them to annotations. I don't have white flowers, I didn't saw enough, I'm not accurate on purple flowers. I want to spend my time and money on those images in order to keep and improve my model. But this process is manual. I can go over thousands of images every week or every month. It's not very practical, so we want a different solution. What we really want is to make this process automatic. We want to develop a new algorithm that will be able to leverage our knowledge regarding the data and regarding the models in order to tell us which images we want to send to annotation and which images we don't want to send to annotation. Those algorithms that helps us to query the model and query the data are called active learning algorithms. And using those algorithms, we can close the loop of the linear process that we saw before. We now have a connection between the models we have currently in production to the new subset that we are going to choose from our unlabeled dataset. This will help us to maximize the improvement and the accuracy of our model while minimizing the cost and the time of the annotations. Before we'll continue to talk more about what is active learning and what are the methods, how we can implement such methods, let's talk about the motivation. Why we want to start this entire project, because it's not even a new feature that we will deliver to our application and to our clients. In my use case, and I'm sorry again for this non-real word, in my case we're talking about medical device and medical data, which means that I can't be wrong for a long time on certain types of wounds or flowers. I need to be able to identify these hard cases and these inaccurate cases fast in order to label them and to keep training using those new labels and images. And the active learning method helps me to get exactly that, to identify the hard cases and the inaccurate cases and to get better improvement on those types. Now let's talk about what is active learning, what is this automatic algorithm that we want to develop. When I talk about active learning, I mainly talk about creating an algorithm which I call data selector. The goal of the data selector is to be able to tell us whether a new image from production will give us an additional information gain when we will train using this image or not. If I can get an additional information gain from this image, I will give it to my annotators in order to annotate it and add it to my training set. And if not, I will just don't use this image. When I started this project, I have 2 or 3 weeks that I just read more and more papers and articles regarding active learning, and I found out that I can divide all the methods that I read into 2 complement categories. The first one talks about data selection, how I can select the data, and the second one talks whether the method that I choose is task agnostic or task specific. Let's start with the data selection. Data selection, we have 2 main approaches for how we can select the data. The first one is called diversity, exactly as it sounds. We want to take a look on the entire distribution of our unlabeled data set and choose diverse data from it. We can take the entire unlabeled data set, divide it into clusters. As you can see here, we have cluster of white flowers or yellow flowers in this case, and then we can choose representatives, 1 or more from each class, and in this way we are making sure that we cover the entire distribution of our unlabeled data. The other option is uncertainty, and it says exactly the opposite. We don't care from the entire distribution. Some of this distribution might be very easy for our model, and we don't want to spend time and money on those parts of the distribution. What we want to be able to do is to identify the inaccurate cases, the uncertain outputs, the places that the model is not good enough on. We want to identify these samples and use only those samples to train again our model. In my case, these are the types of methods that we used in our project and in our research, and we are going to see 2 examples for uncertainty method in the previous slides. Now let's talk about the second category, whether a method is task agnostic or task specific. And again, it's as it sounds, the active learning method can be task agnostic, which means that we can use it for more than one task. We can use the same method for detection and for segmentation, or it can be task specific, which means it is active learning method that can be used only for segmentation tasks and not for the detection. In my case, or in our flowers application, we have several algorithms. 2 of them we already met, which is the detection and segmentation. Detection and segmentation are very popular tasks in computer vision, which means that there are a lot of literature, a lot of methods for detection and segmentation, and as such, we have a lot of literature about methods for active learning, for detection, and for segmentation. But in addition to detection and segmentation, we have some unique features, unique algorithms in our application, and let's say that for this example, our unique algorithm is color distribution. We want to be able to tell our client what is the distribution of the colors inside this flower. This is a unique task. There are not a lot of literature regarding color distribution, and there are no literature about active learning methods for color distribution. What it means that if we are going to use task-specific method, we will need to invent a new method or to make measure changes on existing method each time we have a unique task in our product, and it's not really what we want. What we want is to find a task-agnostic method, one code base, one method that we will be able to apply on every feature that we have in our product, whether now or in the future, and whether it's a popular task or unique task. And again, task-agnostic methods are the tasks that we are going to see later in this presentation, the one that we used in our project. So now let's move on to the method that we try, how we can implement such active learning methods. I'm going to talk about 2 methods that we use in our project. The one is based on the consistency of the outputs of our models, and the second one is based on the loss value of the network. We will start with the consistency-based method, which is based on the paper Semi-Supervised Active Learning with Temporal Output Discrepancy. What does consistency-based method actually mean? It means that if we have 2 models in production, we already trained 2 versions, one that we trained a few weeks ago and the one that we trained 2 days ago. They were trained on slightly different data. We cannot take those 2 models, feed a new unlabeled images into those models and calculate the distance or the similarity between those two outputs. If the distance is small, it means that the outputs are very similar to each other. It means that over time, our model converges about the output that it should give. We can consider this sample as easy sample because every time we train our model, we still get the same output. We don't want to use this sample. We don't want to send them to annotation and keep training using this sample because it will not give us an additional information. In this case, for simplicity, we are talking here about 2 consecutive models, but of course, we can do the research or use 3 or maybe more models in order to really see the behavior over time. In contrast to similar outputs, if we have dissimilar outputs, the distance is high, we feed into both models a new image, we get very similar bounding boxes, as you can see here. It means that over time, our model still didn't converge on the output that it should give. This is an image that is hard for my model. This is an image that I want to annotate and keep training using these images until I get the convergence over time. Now we can take the big unlabeled data set that we have, feed all of it into those 2 models, calculate the distance between the output, and choose the samples that have the highest distance to send to our annotators. Of course, here there is, again, more research that can be done. We do not necessarily want to take the highest distance, the sample with the highest distance. We might want to take some combination, 80% of the highest distance and 20% of the low distance in order to help our network to converge. But this is a further research that can be done, each one in its use case. Now let's talk about the results. What we can see here in the graph. The x-axis is the amount of data we used in this research. The y-axis is the accuracy of the network. The red line represents the accuracy of the network when we sample our data randomly, and the blue line when we sample our data wisely using the consistency method. If we'll take a look on the red line, we can see a graph as we expected. More data gives us higher accuracy over time. If we will take a look at the blue graph here, the blue line, we can see that using 40% of the data, we get similar result to use the entire data set that we have. And this is exactly what we want. We want to find a way to choose our data, a subset from our data wisely, and using it, we can achieve same results. Using less data, we need to annotate less and to train our model with less samples. But does this graph tell us the entire story? Does this graph tell us whether our data selector really succeeds to identify the hard cases and the inaccurate cases as we want? And the answer is that no, this graph doesn't tell us the story and the behavior of the data selector, and this is what we are going to do now. We need to take a look behind the scene in order to really understand our data selector behavior. But to do so, we first need to define a ranking for hard sample and easy samples. In my case, for each labeled image, I have 3 different annotations from 3 different experts, and I can use those labels in order to calculate the consensus between them. And if my consensus is high, in this case, you can see I use the intersection of a union measure. If the overlap between the 3 annotations is high, it means that this is an easy sample. I have 3 different annotators that agreed where are the boundaries of this flower. But if the annotators did not agree where are the boundaries, 3 different experts gave me different answers. So this is a hard sample. If it's hard for annotators to understand what is the true boundary of this flower, it's also going to be hard for my model. Using this ranking, we can create the following graph. The y-axis is the consensus between the annotators, and the x-axis is the data set that our data selector chose at each execution between 2 consecutive training cycles. What we can see here, again, the red is random sampling, and it's pretty much a flat line. Just as expected, we choose randomly, we get similar consensus, and the blue line is when we choose our data wisely using the consistency method. What we can see here, if we will take a look at cycles 2, 3, and 4, we can see the expected behavior. At each time point we execute our data selector, the data selector shows the hardest sample that it has at this time point. But if we will take a look at cycle 5, we will see unexpected behavior. At cycle 5, we have harder samples than the sample that we chose at cycle 4. And this is unexpected. We expect to see an increasing graph over time for this entire graph, and not a graph that we see here. So we decided to investigate what happens here, and unfortunately, we found a bug. It doesn't really matter what the bug. In 2 sentences, the bug was in the consistency measure. We didn't calculate it correctly. But the point in this slide is that we must take a look behind the scene. If we will just take a look on the graph of the results over time, we will not be able to understand whether our data selector really chose and identified those hard samples. It's not the first graph that it saw, it's not enough to understand all the components that we have in this system. Before we move on to the second method, let's talk about pros and cons of this one. The main advantage of this method is that we don't need anything else besides the current model that we have or already trained for production. We don't need to train anything, we don't need to find new algorithm, we can just use what we already have. The disadvantage of this method is that it might be task agnostic, but we still need to understand what the method and what is the task that we face here. We need to define the consistency measure, we need to define this function, and it might be easy for some cases if we have segmentation, if we have one object, but in some cases it might not be that straightforward to define what is the consistency measure for this task. And I had a bug in this, so it might not be that straightforward. Now, let's move on to the second method. In this method also, I will introduce the method, we'll go over the results, and see all the components of this project. This method is a loss-based method. This is based on the paper Learning Loss for Active Learning. And before we talk about the method itself, I will explain what is loss function and loss value, so we will all be on the same page regarding this method. When we train a network and train it in a supervised manner, we have both the input, in this case the image, and a label, the ground truth. When we train the network, at each iteration, we feed the network with the image and get a predicted value. Now, using this predicted value and the ground truth that we have, we can calculate the error of the distance between the prediction and the ground truth. We calculate this error using what we call loss function, and the output of this loss function is what we call the loss value. If our loss value is high, it means that our error is big, and if our loss value is low, it means that we are pretty accurate. The problem with this loss value is that we can get it only while we are training our network. We don't have the ground truth in production or in inference time, so we can't use it in order to understand what is the amount of our error. What we would like to have is a method that will learn to predict the loss value if we had the ground truth label at this time. Now let's see this method. In this case, again, we are with the detection. We have the regular detection network, and you can see here that low loss value results in good bounding box and high loss value results in inaccurate bounding box. What we can do is to attach to the detection network a new network, let's call it the green network, that all its purpose is to learn to predict the loss value at each iteration of this detection network. And you can see here in the example that low loss value of the detection network should result in low predicted loss value of the new network. When we train the detection at each iteration, we feed the image, we get the predicted bounding boxes, and we use the loss function to calculate the loss value using the ground truth bounding box. Now we get the loss value of the detection, and this is now going to be the ground truth label for the green network for the loss prediction. At each iteration, we will have the ground truth for the loss prediction network using the loss value of the detection. Using the loss prediction, the ground truth from the detection, and the predicted loss from this green network, we can also calculate the loss value of the predicted loss network. Later, after we finish train everything, we can take only the green network and use it in production. What we can do now, we can take this entire unlabeled dataset, feed it into this green network, and choose only the images with the highest loss value to send to annotation and keep training using those images. Pros and cons of this method before we are going on to the results. The main advantage of this method is that it's really task agnostic. Every network that we will train have this loss function and loss value, which means that we can attach this loss prediction network into any network that we want. The disadvantage of this method is the overhead that comes with it. We need to train this model for every task that we have. We need to find the parameters for every task that we have. And this is an overhead that we does not necessarily want in our project. Now let's go over the results. This is a similar graph to what we saw before. The x-axis is the amount of data, and the y-axis is the accuracy of our network. The red line is when we sample our data randomly, and the blue line is when we sample our data using the loss net prediction network. What we can see here is that using 60% of our data, we get similar results to use the entire data set. And again, this is what we want. We want to find a way to wisely sample our data, so we will be able to use less data, less annotation, and get same result as using the entire data set. In this case, too, we want to understand the behavior of our data selector, just as we did before. And in this case, we will take it even one step further in order to understand where our improvements come from, whether we really improve and identify the hard cases, or whether our improvement just comes from additional improvement in the easy samples. Let's start with our data selector. Just a reminder, the consensus between the annotators helps us to rank easy samples and hard samples in our data set. And we do it using the consensus between the three annotators that we have for each sample. So this is, again, a graph similar to before. The y-axis is the consensus between the annotators, and the x-axis is the subset that our data selector chose at each iteration that we executed. The red line is, again, random sampling, and the blue line here represents the loss prediction network. And we can see here the expected behavior, exactly what we want. We get a graph that increases over time for the entire graph, which means that at every time we execute our data selector, it shows the hardest sample that it has at this time point. So in this case, our data selector behaves as expected. And now let's see where our improvements come from. What we see here, the y-axis is the accuracy of our network, and the x-axis goes from hard samples to easy samples. The red line and red beans represent random sampling, and the blue line and beans represent wisely sampling using the loss prediction network. What we can see here, first, as expected, easy samples will get higher accuracy than on hard samples. But the interesting part that we can see here is that the improvement that we get when we sample our data wisely using the loss prediction network is bigger on the hard samples than on the easy samples. It's easier to see it using this yellow area between the two trend lines. And we can see that we get bigger improvement on the hard samples as we want than on the easy samples that we are already good enough on those type of samples. So we also saw that our learning curve, the improvement that we get, comes from the harder samples. And we actually get the achievements that we want. We identify the hard samples, the uncertain samples for our models. We send them to annotation, and then we use them in order to keep on training, and we really get the bigger improvement on those samples that we wasn't accurate enough previously. Now, let's talk about the key takeaway. I'm not going to tell you which method is the best. It doesn't really matter because it really depends on your data, on your distribution, and on your use case and product. What I want you to take from this talk, and what really matters here, is that you must take a look behind the scene. Taking a look only on the graph of the final results over time does not tell us the entire story of the system, does not tell us the behavior of the components that we have here. We really need to take a look behind the scene to understand the behavior of our data selector, to understand where our improvement comes from, in order to really understand what happened in this entire system and to understand whether we are meeting the requirements of this big feature and this big project. Thank you very much for listening. I hope you find it interesting. I think we have several minutes for questions, and you can find me here later or reach me on LinkedIn, mail, or my personal website. Thank you. Questions?
Okay, I guess no questions. Thank you so much for the
Thank you.
presentation.